All right, and y'all could go back and watch this also too. So this should be pretty much reviewed. The early history, this early history of chemistry, atoms, molecules. Today is relatively easy. Early history of chemistry, you know, we're going to quiz over this. Greeks first to explain why. You had the four elements: air, earth, fire, and water. Those are the four elements they thought they had. Democritus was the first person to come away from that. Democritus was actually jailed. Did I tell you all that last year? I did or did not? Yes, he was jailed for his beliefs. And he described atomos, small indivisible particles, and proved to be almost correct. Alchemy turned cheap gold into metals, took over about 2,000 years. I need to move that so it's not in the way. So that is alchemy. Now, why was that so important? Because gold was the currency, okay? So that's the way that they would steal gold. They would steal money. They would just make gold, and they would sell it like that. Also, a big thing with that, when you talk about the Middle Ages, you had a sword. So everything you really dealt with was metal. That's why metals were so important then. George Bauer had metallurgy. That's what we're leading into. Swords, I can't ever help but think, when I think of metallurgy, I don't know, I'm older than all you people. Ever watched the Robin Hood with Kevin Costner in it? Well, in part of that, the sheriff locks all the blacksmiths down in his basement because he wants a stronger, lighter sword. Well, Kevin Costner has, I guess, his dad's sword, big, heavy thing, and the sheriff, when they're fighting, with his light, heavy-duty sword, cuts Kevin Costner's sword in half. That's what metallurgy was. Then Paracelsus was medicine. We're talking more about herbal medicines at that point in time, but still medicine nonetheless. Robert Boyle, that should ring a bell. Boyle's law from the first quantitative experiments. Pressure and volume are inversely proportional. This is when Greeks died. The Greek elements died. And then combustion was the focus of the 1600s and 1700s. Lavoisier is credited with the law of conservation of mass. He was actually the one who studied combustion. He studied combustion and found that, yes, in fact, the mass doesn't change. The volume changes very much. He wrote the first chemistry textbook and is the father of modern chemistry. Something I would keep in mind in this is you're going to have a research paper to write, a 10 to 12-page research paper in the month of September, okay? And your options, it's not like last year. Last year you had those, I guess, 30 topics you could pick from. You get to pick someone or something and write about it, okay? Lavoisier is a person people write about all the time. I probably had more papers over Lavoisier than anyone else. Robert Boyle's been a big one too. But any chemist or chemical you can write about. Let me find my mouse. Lavoisier is known as the father of modern chemistry. Wrote the first chemistry textbook. Law of conservation of mass. All right, Dalton's atomic theory. Now, this is a little bit different from last year. Last year, we learned, I think, the 5 different ones, correct? 5 different postulates. I think this one's in 4. Elements are composed of small indivisible particles. Atoms of the same element are identical. Compounds are formed when atoms, we learned 5 last year. Compounds are formed when atoms combine and reactions involve the rearrangement of atoms. Number 1 was split into 2 things. Elements are small particles, and then elements are composed of indivisible atoms. Are any of these true? 100% true? Well, there's one of them that's true. There's only one that's true. 100% true. The only one that's no. It's 3. That's the only one that is 100% true. Now, number 1, why is number? So that's number 2. Number 2, isotopes. Now, for all intents and purposes, are they identical? With the exception of the radioactive ones, yes. I mean, can you tell whether you're writing in carbon 12, 13, 14? No. Can you tell what oxygen you're breathing? No. So for the most part, number 2, they're identical. They're not identical as their isotopes. They have different masses. But for all intents and purposes, they're relatively identical. Why is number 1 not true? No. That's not saying it's the small list. Are atoms divisible? Yes, the hydrogen bomb. Okay, so that's a nuclear bomb. A hydrogen bomb is what makes number 1 incorrect. Now, if you think about John Dalton, this was, I think, the 1600s, okay? This was the 1600s. So when you're really stopping and thinking about it, you know, it took 1940s to figure out the first bomb. You guys were more educated than John Dalton. I told you all that last year. He had an 8th grade education, and he was a teacher. But to come up with that, he was very true. And number 4, we haven't actually talked about. That's something that'll be new this year. It is mostly true. But where it's not true is it actually can also involve the rearrangement of electrons, okay, in a redox reaction. That is where that is different. And most of the time it is atoms, but it can actually be broken down into electrons. All right, next thing you know you're good with, we're not that concerned about, 3 subatomic particles, proton, neutron, and electron. Protons are positive, electrons are negative, neutrons are neutral. Now, what's heavier, the proton or the neutron? No. Relatively, I mean, yes, they are, but no, they're not. The neutron is slightly heavier, okay? I don't remember the exact numbers. I can pass out your chemistry books now and we can go over that. The neutron is slightly heavier, not that big a difference than AMU. If you look at your book, the neutron, yeah, you won't need to bring it every day. The neutron is 1.6749, okay, and the proton is 1.6726, okay. So it's very slightly different. You won't always need to bring your books, okay. I can tell you, I will use some homework out of these, okay. So these are more of a resource. In this unit, we will use some homework out of this. So that's your book. It's actually, if you want to go to CMO and take CH-185, which is the chemistry for majors, chemistry class for majors, that's your textbook, okay? And we know that the proton and the neutron are in the nucleus. Discovery of subatomic particles, we've all talked about this before. The electron was the cathode ray tube experiment performed by J.J. Thomson. Had high voltage rays was passed through a tube, and the rays act like negatively charged. And they noticed we put a negative charge to it, it went away. Positive charges, they came to it because they knew like charges repelled and opposites attract. Plum pudding model was his. We did talk about this last year, didn't we? Early, like I think it's chapter 3 in our other book. Early plum pudding model. Plum pudding is exactly what it is. It's a plum with pudding around it. He came up with that, and he said that the plum was the nucleus, the pudding was the electron cloud, and he didn't really describe anything other than that, other than saying the electrons surrounded the nucleus. The oil drop experiment was Robert Millikan, 1809. So about 10 years later, the charges were thing. He calculated the mass of the electron. The mass of the electron is 1 in 1,840th of a proton. Okay, so it's extremely small, but he calculated the mass of it. The proton was discovered in the gold foil experiment by Ernest Rutherford. After the electron, it always amazed me that the electron was found first. He shot helium at a thin sheet of gold foil. He expected them all to pass through, and most of them did, but some of them were bounced back. And so that he concluded there was a positive center with electrons surrounding the nucleus. This animation doesn't work. So isotopes. Atomic number is Z is the number of protons in an atom. Mass number is A, it's the number of protons and neutrons. Mass number is protons plus neutrons, so you can rearrange that to find either protons or neutrons. Isotopes, atoms, the same element, but with different number of neutrons. And finally, mass numbers are different of isotopes. I'm going to back this up. Who found the neutron? I missed that part of it. Who found the neutron? Anybody remember that? This was always the bonus question. James Chadwick was responsible for finding the neutron. We never wrote about him, but he was in one of those worksheets we did. Was on that we had to read about James Chadwick found the neutron. Not as, I mean, the neutron's not as important, okay? The neutron just kind of filler space in there in some ways. It makes a difference, some isotopes. This is where, in nuclear chemistry, is where the neutron becomes important, okay? Because most of the time it doesn't matter. You care about the number of protons, determines the identity of the element, the number of electrons determine how well it bonds, okay? The neutrons don't always have something to do with it, but we're going to find out tomorrow how they really affect it. Where's my mouse? Nuclear symbol, mass number on the top, atomic number on the bottom, element symbol. Example of that is this. So how many neutrons does this have? What? How many neutrons would this have? How do you find the number of neutrons? Mass number minus protons. So it would be 23 minus 11, so it would be 12. Okay. That's how you find the number of neutrons. Top number minus bottom number. No. In a neutral atom, protons and electrons are the same thing. And neutrons are mass number minus protons. So give you mass. What? Atomic number is number of protons. So 11 is in there. Now, this 11 is not always going to be there. Okay, why is the 11 not always going to be there? Well, the sodium gives away that it is 11. So if people get lazy, they don't put that extra little work, put that subscript in there. It's element number 11 on the periodic table. So whatever, you know, if it was oxygen, they could have 17 and just O, and you know that oxygen has, yeah. All right, radioactivity, that's what we're trying to get into. Radioactivity is defined as a spontaneous decay. Chemical, here we go. This is the change in Dalton's theory, okay? We moved it to electrons, not just atoms. Now, if atoms move, electrons move too, okay? But they want to do it. And also, nuclear reactions involve the rearrangement of the nucleus, okay? Nuclear nucleus. So radioactivity deals with the nucleus. It's a very different way. We won't balance traditionally, okay? When it comes time to balance, we will not do it. Here's the big thing. The mass numbers and atomic numbers on each side must equal, okay? Must equal. It's really more of a tomorrow thing. Important uses of radioactivity, they use them in weapons, okay? Whether it be an atomic bomb, which is a fission bomb, or other things. So how else could, without looking at this, what else where else can radioactivity be used? Power, certainly. That's a big one. Energy, okay? They actually have a nuclear power plant in Paducah area, the Western Kentucky Gaseous Diffusion Plant. They have a big one there. It's now, is nuclear power safe? It's extremely safe. It is the safe. There are less accidents at a nuclear power plant than there is a traditional one. However, the difference is when there's a problem in a nuclear power plant, guess what? It becomes a ginormous problem. What's the most famous nuclear accident? What's the most famous nuclear explosion? Not Hiroshima and Nagasaki. Hindenburg. Ever hear that?
I didn't think that's what it would be.
I'm sorry, that's wrong. Where's the? Yeah, that's wrong. What am I thinking about? It's not Hindenburg. What am I thinking about? Like it's in Eastern Europe. Well, I'm feeling dumb right now. No, I'll come back to that. I can't think of it right now. But it's very safe. Okay, medicine. They use medicine, especially if they use, if they inject a dye in you somewhere, you ever been somewhere they inject a dye, that's typically a radioactive isotope. Is all radioactivity bad for you? No, it's not. Schools can buy sodium as a stable isotope. Well, not stable, but it has one that doesn't actually hurt you. Where else is radioactivity used in medicine? And medicine, MRIs. Remember we talked about that last year. It is a nuclear magnetic resonance was a thing, and then an MRI does the same way that does an NMR machine. And then carbon dating. Think about how something old is. Mm-hmm. But no, that's something different. MRI. If you ever get an MRI or even an X-ray, okay, that's dealing with radioactivity. The mass defect. The mass defect. What is a mass defect? Okay. Oh, but you have it's the saying that the mass of the nucleus is less than what it's supposed to be. Okay? It's less than what it's supposed to be. Some of the mass is converted to energy, called the binding energy. What's this famous equation? It's probably the most famous equation in the world. The mass defect equation. What is it? That uses the mass defect. Everyone knows it. Nope. William Sharp. Most famous equation, E equals MC squared.
Well, I don't think I've never heard the word mass defect.
Because that's the M. Okay, that is the M in the mass defect. Okay, if you have high binding energy, it's stable. Low binding energy, it's not. Mass can be converted to energy, vice versa. Okay, so this is how they figure out how powerful a nuclear bomb is going to be. The greater the mass defect, guess what? The more energy it has. Okay, the more energy it has, and that's what we're going to talk about today. So we're going to find the mass defect. So this is where you're going to need your book. Okay, this is where you're going to need your book, and you're going to need the masses of the protons, neutrons, and electrons. Okay, the masses of the protons, neutrons, and electrons. All right, so let's calculate the mass defect. So here's the big thing you want to take away from this. Here is going to be, all right, let me copy this. How can I not copy this? Copy, Control C. All right, so here's your equation. You're probably going to want to write it down, okay? Right here, this is your equation right there. Yes, just over here where I got it right here. And you might want to write down, it's the same thing on both sides. You might want to write down, you got the equation, what all these things mean too, okay? And it has our mass in there already in AMU. So I think that's an excellent thing to have written down, okay? That's an excellent thing to have written down. The change in mass, that's the mass defect, is equal to the atomic number, the mass, parentheses, mass of protons plus mass of electrons, plus the number of neutrons. That's what A minus Z really is, the number of neutrons times the mass of the neutron. All that subtracted from the actual mass of the atom. Where do you find the mass of the atom? I don't know. I think I can. Yes, ma'am, I can. Yes. Oh, yes, ma'am. This one. And I would probably write all of this stuff down too. Yes, ma'am.
What's it, a
P match the proton.
So P plus ME,
Close parentheses.
so plus, another parentheses, A, is it minus Z?
A minus Z. That's also known as the number of neutrons, okay?
Plus parentheses, M.
No.
What's that?
Times parentheses A minus Z, close parentheses, match the neutron. Illman.
ME,
Mhm.
okay.
Match the
Then
neutron.
close the bracket.
Right.
And then it's minus M.
Mhm. We're actually going to work that example first, okay? That example right there is the one that we're going to work. Calculate the mass defect for lithium-7. The mass of lithium-7 is 7.016003. So you don't need paint. Let me know when y'all are ready, and we will.
All we had to do was write the formula.
Yeah, I would probably write what those things mean too, in case you don't know. Okay. The where. And now I will say this: this is all y'all have access to the recordings. Okay, so if you want to go back and check this for your homework tonight, by all means, you can go back and check that for your homework tonight.
So I'll go back and write all that.
Yeah. All right. So now, but do write. Let's work the example out. Okay. Let's work the example out. Calculate the mass defect for lithium-7. The mass of lithium-7 is 7.010 or 7.016003 AMU. Right below it. Let me find my mouse.
Okay.
Yeah.
Yep.
They won't replace my bulb until the school pot. They won't replace my bulb until the bulb actually blows. It tells me every time I turn it on, please check the lamp, replace the lamp. It's been saying that for 2 years. Lithium-7. Chernobyl. How dumb am I?
What do you say? What was it? Hindenburg?
What?
You said the Hindenburg?
Yeah, Hindenburg explosion. I was back.
That was the gas.
Yes. Yes. That jump at the very end, 7.0. Let me know when y'all got that written down. I'm gonna pull my paint up because my smartboard doesn't work, and I will pull my paint over there to actually work this out. That's the equation that we're using. And I'm going to add another question to this when we're done with it, okay? So, we good to go? Pull that other screen up. Share. All right. So, we have our equation, and we have our equation that we just wrote down. And so you have that equation. And I'm going to put it over here that way I have access to it. So the first thing we need to figure out is the change in the mass. So delta M. Where's my mouse? So delta M. Why is that not working now? It just was. So delta M equals. All right, what is the atomic number? What is the atomic number? 3. It's element number 3. 3 times, and then parentheses, What is the mass of the proton?
How you gonna do
Lithium's element 3 in the periodic table.
it? Okay.
What's the mass of the proton?
The man,
We want an AMU. Yep.
they said it's going
No, of the proton. Of the proton. That was on your thing. I'm sure you didn't write down. Okay. The 1.07. I'll write it down for you. Okay. But that's where I got that number from. Okay. 1.007. I'm pretty good with this. 2, 7. I mean, about as good as I write on the board. Okay. Plus the mass of the electron. Once again, we're dealing in AMUs. Okay. You can do this in kilograms or you can do this in grams, but our question gave us the mass in grams. I mean AMU. 1 point. Yeah, that's a point. Okay. Plus the mass of the electron, which is a small number, 0.000. How many zeros are there? 2, 3 zeros. 5, 4, 8, 5, 9, 7. 8, 5, 9, 7. Okay. And then we're still in my brackets plus. Okay. What's our next thing? A minus Z. So what's our A? What's our mass number? What's our mass number? It gave it to us the problem. What's the mass number of this isotope? 7. 7 minus 3.
What did you say that was that, or was it just neutron?
Yeah, the mass of the neutrons. Then times the mass of the neutron, which is bad parentheses right there. 1.008,665. So that's everything inside the brackets. And then what's our last thing? What are we subtracting it from? The mass of the atom. I mean, the mass of the atom. So what is the mass of the atom? Nope. Not on the periodic table. What's the mass of the atom? The atomic. It was given to you, wasn't it? It told you in the question. Okay, it told you 7 point. It told you in the question what it was. The mass of lithium 7 is 7.0106. So that's where we got this number from. This number will almost always be given to us. Okay, so 7.0166003. That number is almost always given to us. Okay, it's not our periodic table number. Okay, because the periodic table is the weighted average, and you just put it in your handy dandy calculator. Sure get equal oh, two, 1, 3, 2, 5. Is that what you got? Is that what you got? What'd y'all get?
I try to type my whole equation in like once in the calculator. It's part of it.
I would probably have done. You probably missed a set of parentheses. What'd you get?
I don't know.
What'd you get?
0.0569.
0.05. Yeah, I'd say you probably just typed something in wrong there. Okay, that's close to them. Now, my units here, AMU. Now, I could ask one more question about this, and tonight one more question will be asked, okay, on your homework. Can I calculate the binding energy of lithium-7? What's my equation for calculating the binding energy? It's the only equation we talked about today. E equals mc squared. So the binding energy, E equals mc squared. Binding energy is E equals mc squared. And I find the binding energy now? Speed of light. So I'm looking for E. What's my mass or my mass defect? That M is the number you just found. What? Yeah. The number you just found. So 0.04213335. And does anybody know the speed of light? 3.000 times 10 to the 8. Oh, crap. 10 to the 8th. That squared. That handwriting's horrible. I won't do that. Let me erase that and do that again. 10 to the 8th, yeah. I'm rewriting that. Into the 8th. Remember, you're only squaring the speed of light.
Only square the speed of light.
Yep. Not the 0.04. Yep. And what do you get? I have no idea what the answer is on this one. So probably, so you got, I need 3 significant figures. 79 times 10 to the 15th. What answer is this going to be in? Nope. Yep. So that could the question. That's the second. A lot of times that's the, like if you have this on the AP exam, that's the question they're going to ask. Okay. How much energy is available? Okay. And so you got to do your mass defect first, and then plug that into E equals mc squared.